Today we are going to go through a sequence of exercises involving derivatives and tangent lines. I wanted to say that they are all very typical and very common exercises, but I'm not even sure if that's the case. Some of them definitely are, like this one. But there are other things that are going to happen along the way that I'm not sure are exactly typical and common. So I'm just going to say that it's a sequence of exercises that I like very much because the idea is that the level of difficulty keeps getting gradually more, because hopefully if it increases slowly enough, then you get to the end able to do a lot of things that you didn't think you would be able to do in the beginning. So anyway, this exercise is clearly very typical. It's straightforward. Here's a function. Find the equation of the tangent line at a given point, which is x equals 2. And by the way, let me say that the only things that you need to know in order to follow this video, of course, the concept of derivative and of tangent line, but you don't really need to know a lot of rules of differentiation at this point, because all of the examples are going to be like this. All functions that I'm going to put in these exercises are straightforward to differentiate just using the power rule. So that's enough. You don't really need to sketch the graph of the function in order to do this exercise, but here it is, right? X cubed minus x is a polynomial of degree 3. It has three distinct zeros, which are x equals 0, f of 0 is 0, f of 1 is also 0 because 1 cubed minus 1, and f of minus 1 as well. And the point that I'm asking about is x equals 2, which is after all of that stuff. So I'm going to put it kind of here, and that is the tangent line that we want to find. So the first thing that we're going to need for the equation of that tangent line is its slope, and the slope of the tangent line is the derivative of the function at that point. So let's take the derivative of that function. So like I said, it's just the power rule, and this is f prime of x, but what we really want is the derivative at that point, x equals 2. So I'm going to ask f prime of 2 now, and that turns out to be 11. So now I already know that the slope of the line that I want is 11, so I can begin to write its equation. I still need to know this b though, and in order to do that, I want to substitute the value of a point that I know is in the red line. The only point that I know is that one. So the x coordinate is 2 because that's given in the problem, but I also need to figure out its y coordinate, which is f of 2 because it's a point on the line, but it's also a point in the function. So f of 2, which I calculate by substituting 2 into the expression of the function, and that is 6. So now I know that the point 2, 6 is a point on my line. That's what I'm going to substitute in here. X is 2, y is 6. So I plugged in the 0.26 here in the equation of the line, worked it out to see what b needed to be, and it turns out to be negative 14. Just don't forget in the end to write your final answer as the equation of a line, which was what the problem was asking you to do. You just put the negative 14 back into here. Exercise number 2, also extremely common, asks us to find the local maximum. This is the same function as we were just working with. And I'm not going to put the sketch of the function back here because I want to pretend that I don't know how to sketch it, so that I can develop the skill of how to do this in situations where I don't know how to sketch the given function. But this is what a local maximum looks like. This is just part of the function. And what we know about that point in terms of the content that we're currently studying, which is derivatives and tangent lines, we know that because it is a local maximum, then its tangent line is horizontal. That's because the tangent line to the function at each point increases or decreases with kind of the same speed as the original function. And the local maximum is not increasing or decreasing. It's a turning point, so it's a stationary point. It's not going either way. So the tangent line is also not going anywhere. It's just a stationary line, a constant function, horizontal line. There's a lot of synonyms for this. And the slope of a horizontal line is 0. So in other words, when I am looking for a turning point, I am looking for the values of x where f prime of x is going to be 0. And I don't know if that's just me, but when I'm first teaching this content to students, a lot of them look at this and they find it really, really interesting. It's like, wow, that is such a great idea that we can use the fact that the tangent line is horizontal in order to put a number to it, and then from that find the value of x that is the local maximum. This is incredible. So far, so good, right? This is a good reaction. But then they go on to say, but I would have never thought of that. And here's the thing, you guys, this is not the sort of thing that we as teachers expect you to think of. This is the kind of thing that we tell you, and we just expect you to not forget. Because this is really, really common. It happens a lot. We are going to ask you to find local maximum a lot of times. It's a very typical calculus exercise. It's the most typical calculus exercise that there is. So it's not one of those instances where you're supposed to figure things out for yourself. It's a fact that we're telling you. But just be careful not to memorize too fast. You need to feel this surprise and this amazement with this fact a few times before you start to make it into a mechanical thing, find derivative equal to 0. Because if you do it too fast, what I've also seen happen a lot of times is that in the previous exercise, which was just find the equation of a tangent line at a given point, people start to automatically, like, every time I take a derivative, I need to set it equal to 0. And that is not correct, okay? Every time that you take a derivative, in order to find a local maximum, then you're going to set it equal to 0 because of this horizontal thing here. But it's not the case that every time you take a derivative, you're then going to set it equal to 0. That is the wrong thing to memorize. You do have to memorize something, which is the fact that tangent lines at turning points have slope 0, but that's not the same to say every time that I take a derivative, I have to take it equal to 0. In this case, though, yes, we do. So let's do the derivative of this function, which we already did in the previous exercise. Let's set it equal to 0 and then solve this equation. Never forget that when you take the square root on both sides of an equation, you need to add this plus or minus here. But now you have a problem, right? Because you found two answers, and hopefully only one of them is the local maximum, which is the way that the question was phrased. When I say the, it's implied that there's only one, there's not two. But there is also a more general thing to notice here, that we could never find two different turning points and have them both be maximum. Because if you have a maximum and then you turn around and then go back up to turn around again, so that's a second local maximum, you definitely had a local minimum in between. So where is the third turning point here? Because local minimum also has a horizontal tangent, you see? So when you find two, exactly two, you know that one of them is going to be the maximum, but the other one is not. So how are you going to choose which one of these two is the answer to your question? Sketching the function like we did before is definitely a possibility, but I want to do something else. Local maximum and local minimum, both of them have a horizontal tangent line, but one of them has concavity down and the other one has concavity up. So concavity is given to us by the sign of the second derivative, not of the first derivative. So you can use that to decide which one of these two is going to actually be the local maximum that you're looking for. You have the derivative of the function already. Now just take one more derivative using the same rules, because that is the second one. And now you plug in your candidate points to see which one of them has a second derivative that is negative, implying that it's a local maximum. In this case, it's going to be the negative one, because then it's a negative number multiplied by 6 is still negative, so there you go. This is the x-coordinate of the local maximum of that function, which was what the question asked me to do. So finding local maximum or local minimum of a function is the most common kind of exercise that you'll find in calculus, but sometimes the question is asked in not as straightforward a way as in the previous exercise that we just did. This is one of my favorite exercises. It doesn't say maximum or minimum, it doesn't use that word explicitly, but it is asking about something like that. So you have to read the question to understand. The word that he does use is closest. So that is the smallest distance. He wants the minimum distance. There's the word minimum. Well, okay, minimum distance, but minimum distance between what and what? Let's put the point 2, 2 that he mentioned here because the function y equals x squared is already there. And the point 2, 2 is not a point on that graph because 2 squared is 4, not 2. So the point is under the curve. Let's put it somewhere here. And the point in the graph that is closest to it is probably going to be something like that one. Every point in that curve is called x and x squared, and every point in that curve has a distance to the point 2, 2. But some are bigger than others, and I am looking for the green one, which is the one that has the smallest distance. I'm going to solve this problem in two different ways. First, I'm going to really focus on this distance that I'm mentioning, and I'm actually going to calculate it. So what is the distance between the points 2, 2 and the point x, x squared? It's a very small picture, but you can see a pink triangle there, right? I'm going to use Pythagoras in that triangle. And this distance is 2 minus x because it's the distance between the points is x coordinates. Same thing for the y coordinates here, makes it into an x squared minus 2. And now just Pythagoras. That is what Pythagoras is giving me. If I wanted to make just the distance into the subject of this equation, I would still have to take the square root on both sides. But I'm not going to do that for two reasons. First of all, is that this would complicate the function of x that I am currently looking at. This one is very simple. It's just a polynomial. And then if I put a square root over there, it is not going to look as nice. And the second reason is that I don't really need the distance function. Having the function that is the distance squared is going to be enough because what I'm trying to do is to find the minimum distance. But the minimum of the distance is also the minimum of the square of the distance, right? When we're talking about positive numbers, the bigger the number, the bigger the square. So it's equivalent. I'm going to find the same value of x. And yes, this is a brilliant idea. This is not something that I would expect you to think of all by yourself. But problems like find the smallest distance are very common. So what I do expect you to do is not to figure this out on your own, is to learn what I'm just telling you, that this is a possible strategy to solve this kind of problem so that the next time you face a problem that asks you for the smallest distance, you not figure out, but remember that this is a possible strategy. So I'm calling my function g. I am just expanding these squares. Now I'm going to organize it a little bit by collecting like terms. And now I'm going to take its derivative. Why? Because this is one of those exercises, just like the previous one, in which you have a function and you want its turning point. I remember that whenever I have that kind of situation, I am supposed to remember that the function has a local minimum, and the local minimum is a horizontal tangent line. So horizontal lines have slope 0. So I want the slope of the tangent line to be 0 at that point. And the slope of the tangent line is g prime. So I'm going to set this equal to 0 now. Yes, there was a lot of words that I just said, but I wanted to repeat myself to help you to record that sequence of thoughts in your mind. In principle, this doesn't really look like an equation that I know how to solve. I am going to divide both sides by 2 because why not? But that doesn't really help. So just write this down somewhere so that you remember when I erase it, and I'm going to show you a second strategy. But I also want to mention another common misconception here, and hopefully you're going to react to this by saying, what? No, I would never think that. Yes, that is the good thing. But some people do get confused at this point as to why are we looking for a local minimum if we know that the local minimum is there. But like, I hope you weren't thinking that, but a lot of people do. That's a different function, okay? The question was not find the local minimum of this function. The question was find the local minimum of the function which represents the distance between points in this function and this other point out here that has nothing to do with the function. So yes, it is the local minimum of a function, but it is another function. So in case you were feeling that difficulty, the only thing I can tell you is to take a deep breath and read the question over as many times as you need throughout the process, because sometimes you read it in the beginning and then you start doing things, and then at some point you kind of forget where you were coming from. That happens to me too. It's really common. So when you start to kind of feel lost, like I've done a lot of algebraic manipulation here, so that is classic for me to forget what I was doing when I get too involved in the mechanics of it. So you found something, you did a calculation, it's okay, go back to the beginning, read everything again, remember why you were doing these things. Anyway, this equation is disappointing because I don't know how to solve it. Let me erase this and try a second strategy. So the other beautiful thing that we know about shortest distance, and this is really specific, but there is this thing that we know about shortest distance, which is that it needs to be on a perpendicular line. For example, the shortest distance from this point to this line is this one that makes this 90-degree angle there. It's not exactly the same over there because being perpendicular to a line is an easy concept, but what does it mean to be perpendicular to a curve or to the graph of a function? So what it means is that you are perpendicular to the tangent line to the function at that point, okay? So the orange line here is the tangent line to the function at the green point, and this green line is perpendicular to the tangent line. What is the name of that? It's the normal line. So in this strategy, we are looking for the tangent line at the function that was given to us. So the function is x squared, the derivative is 2x, and I'm going to change the name of that green point. Instead of calling him the independent variable x, I'm going to call it a fixed value that is still a letter. I'm going to use the letter P for point, but of course you could use any letter that you want. And the reason why I'm doing this is because I want to avoid confusion between what is x, the value of the unknown value that I want to find, and what is x, the independent variable of a function. So there's two different x's here. I don't want to confuse one with the other. So from now on, x is the independent variable of my function, and p is the unknown value that I am trying to find. P is the x-coordinate of the point in that function that has the shortest possible distance to the point 2, 2. I know that f prime of p is 2p. I know that 2p is the slope of this tangent line, but I don't want to talk about the tangent line. I want to talk about the normal line, and they're perpendicular. So what is the slope of a perpendicular line? It is minus 1 over the slope of the first line, right? So this is the equation of the normal line, but it's not finished because I don't have this value of b yet. And in order to find it, I can substitute a point. Remember that something very similar to this happened in the exercise number 1, where we were also looking for the equation of a line, but we had the slope and we still didn't have the y-intercept. So we took a point that we knew in that line and substituted its coordinates in x and y. I still remember the numbers. They were 2, 6. It was the only point that we knew for the line at that situation, which happened to be the point where the line was tangent to the function. So it was a point in the function. In this case, we don't know what the coordinates of the point in the function that make this normal line are. That's what we're looking for. We don't know it. But we do know one other point in that normal line. It is the point 2, 2. So that is the point that I'm going to substitute here. So x is 2, y is 2. This 2 cancels with that 2. So b is 2 plus 1 over p. And plugging that back into the equation of the normal line, we get this. But this is not yet what we are trying to find, because what we're trying to find is the value of p. So this is an equation that involves p. It looks like it might be helpful, but it also involves an x and a y, so that doesn't feel right yet. I want to substitute something of p in there. And here's the thing that is going to help me. The point p that I am looking for belongs to that line. When the x coordinate is p and the y coordinate is p squared, that's when the point belongs to the line. So now is when I want to substitute the green point into this equation by putting p squared for y and just p for x. Now let's see what I can do with it. This p cancels with that p. Maybe I want to multiply both sides by 2 to get rid of this fraction. Oh, minus 1 plus 4 is 3. And now I also want to multiply both sides by p to get rid of this other fraction. Maybe subtract this so that I get something equal to 0? But this is disappointing because it is the same equation as I had before, and it's not an equation that I'm going to find a satisfactory answer for just using my hands. If I had a calculator, of course I could, but then if I had a calculator, I don't think I would have done so much by hand. I would have gone to the calculator a lot earlier and probably not even take a derivative. I would just have written the distance function, graphed it, and looked for the local minimum. So what am I going to do with this? I don't know, probably nothing. That was not the point anyway. I wasn't trying to find the value of p. I was trying to show you the structure of one type of problem that is very typical. Maybe I shouldn't have chosen y equals x squared as the function for this exercise. I could have asked this question with any function. Just take a function, take a point, and ask for the shortest distance. And other functions that they might give you might turn out to have simpler equations to solve in the end. What I'm interested is in showing you the structure of both strategies that could have been used here. I said in the beginning of the video that this was going to be a sequence of exercises in gradually increasing levels of difficulty. So let's take a moment to explore right now how this has been happening so far. Exercise 1 was more straightforward, where I gave you the point and asked you to find the tangent line at that point, which was x equals 2. Exercise 2, in a sense, was backwards because I was giving you some information about the tangent line, the fact that it was horizontal, and then I was asking you to find the point where that tangent needed to be. And basically, the strategy that I always want people to use when the problem is backwards is to do the exact same thing as you would have done if you knew the value of the point in the beginning. But then, of course, instead of calling it a number, you're going to call it a letter. You keep working with that in the exact same way. And then at the end of the exercise, you're going to have an equation that you're then going to solve in order to find the value of the variable. So in other words, it's not that you try to work backwards. You work forward, like from the point to the tangent line and not backwards. But you start from a point that is an unknown number. That's why variables are an interesting object in math, because you don't know the number, you can just call it a letter and keep working with that. And of course, in the end, you're not going to find a number, but you're going to find an equation, an expression. Then you use earlier tools that you've known for a longer time in order to solve that equation and find what the letter needed to be in the first place. So it's not working backwards. Exercise 3 was kind of the same thing, but the difference from 2 to 3, the reason why it's more difficult, is because the path from calling this a letter, which was p in that case, until we got to the final equation to solve to find the value of p, was just a longer path. The information that was given in that case was not about the tangent line, it was about the normal line, but that's not what makes the difference. The difference is that you had to be comfortable working with a letter P instead of with a number 2 for a longer number of steps before you got to an equation that you could then solve to find the value of P. We are almost at the end of the part 1 of this video. I'm going to show you the questions for the rest of the problems that I have in mind in case you want to give them a try before I post part 2. Part 2 is going to be posted probably in about 2 or 3 weeks, but if you just can't wait to see it, it's already available for channel members. So here's problem number 4. It is the same function and the same point as what we had in the previous one, but now he is not asking anything about distance. Instead, what he is asking is for tangent lines to this function that pass through this point. Problem 5 is this one. It comes with this picture. It comes with the coordinates of this point and this point, which are 0, 2, and 2, 0. It tells us two functions which have four unknown values, p, q, r, s, which they want us to find. And it also tells us that this line that we see in the picture is tangent to both of the functions in both of those points. Exercise 6 is also about two functions having a common tangent. This means that it's one line that is tangent to both functions at the same time. In this way, it's similar to the previous exercise that we were just doing. But now he wants that common tangent to be at a point x equals p. And that is not what was happening in exercise 5, where the line was tangent to both functions but at different points. And now we want the same tangent to both functions at the same point. Problem 7, it is highly unlikely that we are going to be able to find a concrete answer just by hand because it wasn't intended that way. This is a question that is intended for the use of technology. So if the calculations become difficult, let's not worry about that. What we are focusing on is the structure of solving the problem. So by now, because we've been doing a sequence of exercises, we're not just starting in this one. I hope the fact that it's one line being tangent in two places is not surprising anymore because we've seen other examples of how this kind of thing can happen. But this is the first time that we're going to want to find 2 points, and so that is going to make it more difficult than the previous ones.